Okay, hello and welcome to the A-Level Further Maths Revision session for Callum Cymru. My name is Matthew McMillan. I'm a maths teacher at Christ College in Brecon. This week we're going to be looking at matrices. So looking at the specification, there's quite a lot to get through on matrices, but I think by looking just at a few exam questions we'll be able to get through all of this. There's just a few things to spot. For instance, it says we should be able to solve simultaneous equations by use of the inverse matrix and by reduction to echelon form. Just in case they specify you must use this method, we probably need to just check both of those. It also talks about calculating determinants and this thing interpret as a scale factor, including the effect on orientation. Because that's the first thing that they've got in the specification, that's the first thing that I'm going to have a look at now. Okay, so you can see we've got a cube here, and the volume of the cube is 1 unit cubed. We've created this matrix down here, the identity matrix, 1, 1, 1. That's kind of telling us where this corner, you can see where my mouse is, that's telling us where that corner of the cube is. That's located at 1 in the x direction, 1 in the y direction, and 1 in the z direction. Let's double the lengths of each of the sides. So I'm going to pull this to 2. I'll pull this in the y direction to 2. And I'll pull this in the z direction up to 2. The volume of this cube, 2 by 2 by 2, the volume is 8. And you can see the determinant over here of the new matrix is 8. So the determinant is telling us the volume scale factor. Now, let's say that we change this. So let's bring this over to negative 2. We've now got a determinant of negative 8. So it's still the same volume scale factor, but we've changed the orientation of the cube. Effectively, we've kind of reflected the cube in the y-axis here. I could do the same if I pull the y component this way. So I've now reflected the cube here across the x-axis, I guess. And we could do the same in the x direction. So if you do play around with this, if you click once on the coordinate, it changes it from kind of how you can move it. So I've changed the z coordinate now, and that's given us a negative. So if I bring that back up, now if I click once on this, it changes it to allow me to move it left, right, forwards and backwards. What's going to happen that's going to be a bit odd is if I pull this over here, I've got a negative determinant. So I've changed the orientation of the cube. This one here, if I pull this over here, now it's back to being a positive determinant. So we've got some odd stuff happening if we kind of, get a positive determinant or a negative determinant. We need to think about which quadrant this shape is going to end up in. This is actually a rotation of the original shape. We have not changed the orientation. So I'll just sort of pull it back to here. Okay, let's pretend that let's just have a look at this. So there I've changed the orientation of the cube. Okay, I've reflected it. Let's pull this back and we're going to create the same cube over there. Imagine instead that I rotated this cube around the origin here. So this would then rotate around to here. This would rotate around to here. And can you see, because it's a rotation and it's not a reflection, our determinant is still a positive. It's a positive value because we have not changed the orientation. If I kept going with this concept, so I'm going to rotate this around here and rotate this around here, can you see the determinant is still positive because all we are doing is rotating it, we're not changing the orientation. So if it is a positive, it means we haven't changed the orientation. If it's a negative, that means we will have changed the orientation. So if I bring these back to the y and the x, there would be a way then that I could get a negative over here. Instead of, I guess, bringing this over here and this over here, let's say that we switch the x and the y components. So I'm going to bring this way and this way. We have completely changed the orientation, so I guess that's a reflection then to create that shape. So the scale factor, the determinant is telling us not only the scale factor of the volume scale factor, it's also telling us about the orientation of the new shape. Now, thinking about singular and non-singular matrices, a singular matrix is where the determinant equals 0. So what I'm going to do is I'm just going to pull this point down so that it's 0. So we have a scale factor of 0. We have completely collapsed the cube. This is a singular matrix. Okay, so that's a little bit about the determinant and how it affects the scale factor. What we need to look at now is actually calculating the determinant and then finding the inverse of a 3 by 3 matrix and using that inverse to solve three simultaneous equations. So that's what we're going to have a look at next, and we'll do that by looking at an exam question. Okay, so here's a typical exam question. You might like to pause the video now and just try this exam question yourself. Now, singular, that means that our determinant of A should equal 0. So that's what we're going to calculate. We're actually being asked to calculate the determinant of A, or set it equal to 0. And what we're going to do then is we take each of the top rows. So I'm going to take this 2, and then we multiply that by the minor that's created, the minor of the matrix that it creates. So I'm going to I kind of ignore these guys and ignore these guys, and it creates a little matrix down here, and then we find the determinant of this. So 2 times 5, that's 10. Take away 5 times lambda, 5 lambda. So that bit there, that's called the minor of the minor of element 2. Then we're going to do the same process, but we'll do it on this bit here. So we're kind of ignoring this, and we're ignoring these guys here, and we're thinking about this 1 times 5. So we've got lambda times the determinant of this other matrix here, and we're ignoring these two in the middle. So 1 times 5, that's 5. Take away 4 times lambda, because I'm kind of looking at these two guys here. Take away 4 lambda. And then we've got the last one to do. So the last one is going to be this 3 here. 3 times the determinant, and we're kind of ignoring this and this, getting a bit messy now, isn't it? So 1 times 5, that's 5. Take away 2 times 4, take away 8. Now the bit that we need to get right, and it's critical, is the signs. It starts with a negative and then it goes to a positive. So we've got a minus and a plus in that order. If you don't get those right, it's going to go wrong. This should equal 0 because the determinant, it tells us is 0 because it's singular. Let's multiply this out and see what we've got. So we've got 20 minus 10 lambda minus 5 lambda plus 4 lambda squared. And then here we've got 3 times, well, this bit here is negative 3, so we get minus 9 equals 0. And we've got a quadratic which we're going to solve. 4 lambda squared minus 15 lambda plus 11 equals 0. And then your preferred method of solving, this one we can factorise. It's going to be 11 and 1, minus and minus. So lambda is 11 over 4, or 1. So this exam question then continues, and here they're saying that lambda now is equal to 3, and it says find the inverse of A. Again, you might like to pause the video and just check that you can do this yourself. You should note that from part A up here, we had this expression. This expression gives us the determinant of matrix A. Now in our one, because we had a singular matrix, it was equal to 0, but I could just scrap that bit here, and it's going to equal, or whatever it equals will be the determinant. In fact, I could calculate that now. So the determinant of A, given that lambda is 3, is 4 times 3 squared minus 15 times 3 plus 11, and that equals 2. So the determinant of this matrix is 2. Now let's find the inverse. It's probably worth noting down what matrix A is with the lambda replaced for the number 3. So we've got 2, 3, 3, 1, 2, 3, 4, 5, 5. So to find the inverse, I do it in a few steps. Usually I start by finding the minors of the matrix. So let's just do a couple of them explicitly, and then you can work out the rest yourself. I will kind of set the matrix up, and I'll start by taking this 2 here and finding the matrix of that 2. So you kind of cross that lot off, and you cross that lot off, and you're left with these guys here, and you're finding the determinant of this. So it's 2 times 5, take away 3 times 5. So that's 10, take away 15, that's negative 5 for that element there. I will just do one other element because I think it'd be helpful just to do one sort of that's a little bit more awkward. I'll just try and rub off some of these marks. Let's do this one here, this 3. So we kind of cross off anything that's in its column, and we cross off anything that's in its row, and we've created this new matrix. Do you see the 2, 3, the 4 and the 5, and we're finding the determinant of this. So it's 2 times 5, that's 10, take away 3 times 4, so that's 12. So 10 take away 12, that's negative 2, and because it's this element here, it goes in the same place. That should be negative 2 in that position there. I won't do them all because it will be a little bit time consuming. I'll just tell you what they are. Negative 7, negative 3, 0, negative 2, 3, 3, 1. Once we've done that, we'll find the cofactors. And basically, we're going to apply a pattern to this. Apply this pattern. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So we apply that pattern to the matrix we've just created. So this first element says keep the sign. Okay, if it's already a positive, you keep it as a positive. If it's already negative, you keep it as a negative. I can see it's negative 5, so I'm going to write negative 5. The next one, well, this is a negative, so it says change the sign. So if it's negative 7, it's going to turn into a positive 7, and then we get a negative 3, and then a 0, negative 2, positive 2, 3, negative 3, and 1. So those are the cofactors. Next, we find the transpose of this. Transpose. We basically turn all of the rows into a column. So this row here, 5, 7, minus 3, I'm going to turn it into 5, 7, minus 3. I've just turned it into a column. Same here, 0, negative 2, 2, 0, negative 2, 2, and then the last one, let's do it in this colour, 3, negative 3, 1, 3, negative 3, 1. That has a name, and you need to know what this name is. That's called the adjugate. Matrix. Or sometimes they say it's the adjoint of the matrix. That term, the adjugate matrix, you must know it's explicitly commented on in the specification. You could just remember it as the step before the final answer of an inverse, because we haven't quite got the inverse yet. So to get the inverse, we are going to write that matrix that I've just created, 5, 0, 3, 7, negative 2, negative 3, negative 3, 2, 1. But in front of it, I'm kind of dividing by the determinant, so we're going to do 1 over the determinant, that bit there, determinant of A. And that is our inverse matrix. So remember, the step before you get your final answer, that's called the adjugate matrix, and you will need to know that. So that's the inverse of matrix A. Okay, so this question continues. You might like to pause the video again. It says, hence, solve the equation. So hence means I probably need to use the previous parts of the question. And we notice that the equations presented are basically the same as the matrix, except they equal some numbers. So we're going to need our inverse matrix here. The concept is here that I've basically got matrix A. Remember, these have been replaced for a number. I think they've changed it for a 3. So I'm taking matrix A and I'm timesing it by x, y, z. And that equals 2, negative 1, 4. And the idea is I would like to find what x, y, and z equals. Now, this would be incorrect. You can't divide by a matrix. We can't divide by matrix A to find out what A is. What we do is we multiply by the inverse. If you did this, let's multiply this by the inverse matrix A, that would then multiply this side by the inverse matrix A. That would be incorrect because the order in which you multiply matrices is important. It does matter. So this would give us the incorrect answer. What we need to do, I'm just going to rub that out because it's incorrect. I need to be cancelling this A off, so I am going to multiply by the inverse matrix this side at the front, because you can then see that the inverse matrix here would be cancelling off matrix A. That means that I have to multiply these values here by the inverse matrix at the front because the order is important. So that's what we're going to go ahead and do. So x, y, z equals the inverse matrix 1/2 times, what is it, negative 5, 0, 3, 7, minus 2, minus 3, and minus 3, 2, 1, times 2, negative 1, 4. So that equals 1/2, and we just need to remember how we multiply matrices together, kind of a topic you do in year 12. Remember, you're kind of taking each of the rows and you're going to times it by the column. So to get this first element, we're doing negative 5 times 2, negative 5 times 2, and then we're adding 0 times negative 1, 0 times negative 1, and then we're doing adding 3 times 4, so add 3 times 4, that is giving us 2, and if we do the others we get 4 and negative 4. And then I suppose we should multiply by the half at the front, so our final answer here is going to be 1, 2 and negative 2. They're actually happy in the mark scheme to leave it there, but I would sort of err on the side of caution and just say that x is 1, y is 2, and z is negative 2. So that's a fairly typical exam question on finding the inverse and then using that to solve equations. Okay, so that's covered looking at the determinant of a 3 by 3 matrix and then using the inverse of a 3 by 3 matrix. I commented on the adjugate matrix, which you need to know. And we've also looked at solving linear simultaneous equations using the inverse matrix. The thing I haven't done is I haven't done reduction to echelon form, so we're just going to have a look at that now. So I couldn't find any exam questions where they explicitly said to use reduction to echelon form, so I've kind of taken an old question and just added in this statement at the end: solve the equations by reduction to echelon form, just so we can get a bit of practice on it. You might like to try it yourself. I'm going to just rewrite this. So we've got 3, 4, 2, 1, 1, 4, 4, 5, 7. But what I like to do is I just put a sort of dotted or dashed line there, and then I write the 1, 7, 10 here. Like that. That's called an augmented matrix. It's kind of combining 2 in 1. Now, it doesn't actually matter which row we write first. So because I've had a little think about this question, I'm actually going to rewrite this row at the top here. So I'm going to change the order to 1, 1, 4, 7. And then I'm going to put this row kind of second. So 3, 4, 2, 1, and then 4, 5, 7, 10. I'll keep that third row in place. You can double check why it doesn't matter the order. It's basically because when we do multiply this through, so let's say we did 4 times this matrix, you're doing 4x, so you'd be getting 4x, 5y, 7z, and they would still equal the 10. So it doesn't really matter the order you write them in. Now that I've done that, I'm going to sort of refer to this as row 1, this one as row 2, and this one as row 3. And the idea is that I want to use this one here, this number 1, that's going to be our pivot, and it's going to help us get rid of some of the information in the other rows. So I kind of am going to copy across the first row, 1, 1, 4, 7. And then I'm going to start doing a little bit of manipulation to get rid of some of the information in the other rows. So I am going to take away 3 lots of row 1 from row 2. So do you see here we're starting with a 3. If I take away 3 lots of 1, which is on row 1, on the first row here, that should leave me with 0. Let's do the same with this 4. If I take away 3 lots of this 1, that should leave me with a 1. Let's take this 2. If I take away 3 lots of this 4, so 3 times 4 is 12, that should leave me with a negative 10. And then the final bit, I'm starting with this 1, I'm taking away 3 lots of 7, so I'm taking away 21, that gives me negative 20. We'll do the same down here. I want to basically cancel this first one off. So I want to be left with a 0. That's the concept. And so to do that, I can see I'm going to have to take away 4 lots of row 1 here. Let's do the same here. So 5, take away 4 lots of that. So that's going to be a 1. And then we get minus 9. And then we get minus 18. So that's the concept. We gradually want to create zeros in the first few columns. Let's continue. Now we're going to use this one here as our new pivot. So I think I can kind of copy across the top row. We've got 1, 1, 4, 7. And then we've got 0, 1, negative 10, negative 20. And the next one is where I will need to do the manipulation. And we're going to put our little dashed line in there. So I'm kind of thinking what I need to do is I need to get rid of this 1. I need to turn it into a 0. So this is already a 0. So that's going to go there. This next one, I need to turn it into a 0. To do that, I just took away row 2, just one of row 2. Here I've got -9 and I'm going to take away -10, so I've got to be careful there, that's going to be +1. And then here, -18, take away -20, so that's actually +20, so that's going to give us 2. What you can see then is we kind of have this nice echelon shape. This then is called row echelon form. Echelon is, I think it's French for rung of a ladder or step of a ladder or something like that, so it creates this kind of step shape. This then allows us to create 3 equations. So we have, if I look at this top row, we've got 1x plus 1y plus 4z equals 7. That's not very helpful. The next row though is 1y minus 10z equals -20. The third row is the most useful one because I can see I've cancelled all the x's, cancelled all the y's, and I've just got 1z equals 2. So I know z is 2. Then I'm going to take equation 2 that I've just created. So that's y take away 10 times 2 should equal -20. That gives us y as 0. And then let's take equation 1. So x plus, well, y is now 0, plus 4 times z, z is 2, equals 7. So x equals 1. So that's solving an equation by reduction to row echelon form. Okay, so that's a little bit about solving equations using matrices. Now, to finish, we're just going to have a think about the solution of simultaneous equations and thinking about them on a graph and how they might create a plane, and thinking about unique solutions, non-unique solutions, and systems that are consistent. Also thinking geometrically what is going to be happening with each of these situations. This final question kind of looks through all of those things. Okay, so here's a question that's looking at whether a set of equations are consistent or not. So let's just remind ourselves what that means. Now I've stolen these images from a textbook that I've got. Consistent equations means that we're going to have at least one solution. So you can see here, the first image here, we've got a solution where the 3 planes intersect as a single point. In the second image here, we must have a solution anywhere along this line. Okay, that's called a sheaf. And then the third image here, well, that's just where 3 planes are just kind of sandwiched on top of each other. This one here, the third one here, you are very, very unlikely to get that, because that's basically going to have 3 identical equations, or equations where one's a multiple of the other. For inconsistent equations down here, the first situation here, you can see you've created a prism. Okay, we've got a triangular face here, and it's a triangle all the way through the shape, so it's a triangular prism that we've created, and we don't have a point at which these planes all meet. Like, yes, I can see the green plane and the orange plane are meeting here, but the blue plane does not meet them there, so that's inconsistent. The second image here, I can see that 2 of the planes are parallel, the orange plane and the blue plane, so I can see that I've got, yes, there's going to be solutions there between the blue and the green, but the orange plane is never going to meet that. And then the third image here, that's where all of the planes are parallel. Now, just looking at this question, find the general solution for this. That is kind of directing me towards this situation, because firstly it says they're consistent. If there's a general solution, it probably means that as we vary our value of k, we're going to be moving somewhere along this line, and so the general solution is giving us a point anywhere on this line, and we'll have a look at that in a minute. Okay, so let's go ahead and actually solve this question. You might like to pause the video and just have a go at it yourself. Determine the value of k for which the following system of equations is consistent. Now, if I took this matrix and I found the determinant of that matrix, if that did not equal 0, so if it was non-singular, that would be consistent. And the situation you would have is this situation here, where you would have one single solution. The planes would meet at a point. In this situation, though, the determinant of that matrix is equal to 0. That means we need to do a little bit more work to see if they are consistent or not. There's another little thing here, because it talks about the general solution. That means we're sort of looking really probably at this situation. So we'll go ahead and start solving this. I'll take the matrix and I'm just going to rewrite it as an augmented matrix. So 1, 2, 3, 2, 3, 1, 3, 4, -1, and then I'm going to write the solutions 2, 3, and k as my augmented matrix, and then I'm going to start to reduce this to echelon form. So let's keep the top row. 1, 2, 3, 2. There we go. And then I'm going to take away, I think, here, take away 2 lots of row 1. That's going to be our pivot. So we get 0, -1, -5, and -1. And then here we're going to take away 3 lots of row 1. Take away. So that's giving us a 0, which is what we wanted, -2, -10, and k minus 6. And then we can kind of pause here. So for consistent equations, because we know there's not going to be one single solution, what we're interested in is we're looking to see if this row here is a multiple of the row beneath it. And this is looking good here, isn't it? Because that, if I times that by 2, that seems to work. If I times this by 2, that seems to work. So that it kind of implies that if you times this by 2, that's what we're looking to achieve. And that would then, we could then say that these equations are consistent. So that allows me to write down a statement then that k minus 6 must equal whatever -1 times 2 is. Well, that's -2. Therefore, k must be 4. So that's found our value of k. We'll have a look at this on a graph in a moment. Let's just continue and do part B. So for part B, find the general solution of k, because for this value of k, because we've got like it could be that that's a coordinate, or that's a coordinate, or that's a coordinate. We've got loads of coordinates all along this line. You've got an infinite number of coordinates. We want a general solution for that coordinate. So what we do is we let z equal just a variable. We're going to call it variable alpha. And then I'm going to take row 2 from here. So I can see it's 0x minus 1y, so minus y, minus 5 times z, but z is not a z anymore. I'm going to use the variable alpha equals -1. So minus y must equal 5 alpha minus 1. So positive y must equal 1 minus 5 alpha. Let's do the same for the top row, row 1. So this one here, that's 1x plus 2y. Now y, I'm not going to use the letter y anymore. I'm going to use what I just created, which is 1 minus 5 alpha plus 3z, but we're not using z anymore, we were changing it to alpha, and that equals 2. Let's multiply out this bracket, so we get 2 minus 10 alpha plus 3 alpha equals 2. And then if we rearrange this and tidy it all up, we get x equals 7 alpha. So those are our general solutions. General solution. If we think about what this would be, this is the x coordinate then would be 7 alpha. The y coordinate is 1 minus 5 alpha. And the z coordinate is just alpha. So that's our general solution. We will now just take a look at what this will look like on a graph. Okay, so you can see I've represented the 3 planes on this graph. At the moment, if I kind of get the view straight on like this, you can see we've created a triangular prism. It's completely hollow throughout. And then over on the left hand side here, I've set my k value. We could change this k value then, and you just want to take a look at what's happening to the plane as I change it. If I put it like that, you probably see it a little bit easier. You see the green plane is just moving backwards and forwards. And the idea is, I think, that to get consistency, that green plane needs to kind of hit the red and the blue plane in the same place. So we got a k value of 4. And there you can see all the 3 planes are meeting, creating this kind of sheaf pattern. They're all meeting at that point. So that's the situation with the k value. That's what that's doing. The general solution then is saying, let's create a coordinate that sums up anywhere on that point. So can you see over on the left hand side, I've created that, instead I couldn't get the alpha symbol, so I've said it's 7a for the x coordinate, 1 minus 5a for the b coordinate, and then a for the z coordinate, 1 minus 5a for the y coordinate, and then a for the z coordinate. If I turn that on, there we go, you should be able to see that dot a, and if I move this now, it should be anywhere on that line. So I'm changing the value of a, but it still creates a point kind of where the 3 planes are meeting, and that's what we mean by a general solution. Okay, so that's the end of the session on matrices. We've managed to go through the entire part of the specification on matrices there. If you want to revise de Moivre's theorem or solving trigonometric equations, have a look at the previous 2 sessions. And then in the final session, it's a live session, and you can come and ask any questions you have on any of the topics that we've covered before. And I'll also be looking at questions involving polar coordinates.